So what is the disadvantage of specifically the MSI protocol? A processor reads a cache line and then writes to it, and assuming that no other core has that cache line. Let us say that a processor P1 is trying to uh, uh, do a read followed by a write to that same cache line, and this is assuming no other processor has that cache line. So this means that it is initially in the I state, it changed to S because it read it, and it changed to M because it wrote to it. Now it is going to send a bus upgrade signal to all the other processors that it is about to write to that block. Because it's a cache hit, it's going to send a bus upgrade signal. Now, the disadvantage or the problem here is that there is no other processor which has that block, because there's only one processor, P1, which has this block, and therefore this bus upgrade signal is not really useful for the other processors. So the cache controller has to keep checking the other blocks, but the other cores, but really there is no other core which has that block. So every time, let's say this processor keeps writing to it or reading from it, it keeps sending this bus upgrade, and all the other processors keep checking it. So this is an unnecessary step here, and the problem here is because we have only three states, we don't have any extra state to indicate that it is only in the current processor. Remember that the shared state indicates that this is in one processor or more than one processor. So this doesn't really tell us whether it is in just one processor or in two processors or three processors. So it's just one state here. So this is the problem, and therefore, in order to remove this or to solve this problem, they introduced one more state which is called the E state. This E state is also called exclusive state. So if at all there was one processor which has this cache block and no other processor has it, then you're going to have the cache block in what is called as the E state instead of the S state. And therefore, there is no need to send this bus upgrade signal if you are in the E state. So this just reduces the number of bus transactions. And this is called as the MESI protocol, MESI, MESI protocol. So the rest of the definitions remain same, modified and invalid are the same. So they introduced an exclusive state. Exclusive means that there is, of course, a valid equals one, and dirty bit is equal to zero. This means specifically for reads, and valid equals one and dirty equals zero. This also means that this is the only copy, and it's a clean copy, and this is consistent with the memory. So earlier you had the shared state. Shared state meant the data is in either one cache or more than one cache. Whereas here in MESI, the definition has changed. Shared state means the block is in more than one cache only, not in one cache, but more than one cache. So this means that it is in one more cache. So the modified state remains the same. Valid equals 1 and dirty equals 1, and it's mainly for writes. And this also means that this is the only copy, the only updated copy, which means we're going to invalidate everything else. So let us run through this sequence for the same example. Again, this is taken from Wiki. You could also refer to Hennessy Patterson, but like I said, it's a little more complex there. So processor read on A issues a bus read on the bus. And since this is the first time and this is the only copy, I is going to change to E. So whenever you have a processor read from I, you're going to change to E. That is, if you see a bus read. So I is going to change to E here in this case, and it's going to read the value from the main memory. Then let's say I want to do a write when it's in the E state. So when it is in the E state, if you want to do a write, it just does a write And remember, there is the hyphen here, which means that there is no bus transaction. There is no signal sent on this bus because it's in the exclusive state, which means this data block is present only in this particular cache and not in any other cache. And therefore, it's exclusively present in P1. Therefore, I don't need to broadcast this message on the bus, and there's no bus transaction. But because I'm doing a write, and the data is inconsistent with the memory. So when it is in the exclusive state and you do a write, you go to change to M state, just like before. So go to change to M state. So there is no bus transaction when you change from E to M state. Now let's say processor 2 does a read. It sends a bus read on the bus. So it's in the I state. So if you have a processor read, you could obviously change either to E state or you could change to S state. So previously, when processor 1 uh, requested for the data, we changed from I to exclusive state. That's because when the bus read happened, the bus read checked the other cores and it found no other core had that, and therefore we changed from I to E. Whereas here, when the processor 2 sends this processor read, there is a bus read here, and this processor 1 sees this bus read. So this indicates that there is one more processor which has that data. And therefore, this I state is not going to change to exclusive state. This I state is going to change to S state. So this I will change to S here. But in addition to that, like before, we also have to see what happens with this first processor when it is in the M state and it sees a uh, bus read signal on the bus. So when it is in the modified state and it sees a bus read on the bus, it is going to change to shared state, and it's also going to write back this data because that was the latest copy of the data, and it's going to send a flush on the bus and update this data in this memory and change itself to S state. So this is how it works. So you could also try out the other cases here. The next is processor write. So when we do a processor write, as before, we are going to, it's a cache hit, therefore it's going to send a bus upgrade signal. So remember, whenever there is a cache hit or a write hit, it's going to send a bus upgrade signal. And whenever there is a write miss, it is going to send a bus read X signal. So since this is a cache hit, this is going to send a bus upgrade signal. And therefore, if it's in the shared state and it's going to write to it, so always remember whenever you do a write, you need to change to modified state. So from the shared state, we change to modified state when we write, and this is a bus upgrade signal. And this processor sees that bus upgrade signal while it is in the shared state. So in the shared state, it sees the bus upgrade signal, and uh, and therefore it's going to change to the I state. So this is entire thing, whether it's a bus read X or a bus upgrade or this other flush opt, which we'll not discuss here because we don't not using it. So it's going to change to the I state. So it changes to the invalid state. So now the processor 2 has written successfully here, and the written value is a equals 2. Sorry, the written value is a equals 3. So now the question for you is, what happens now if processor 1 tries to read? So at this point in time, when this is I, this is M, and this is A equals 2, what happens if processor 1 tries to uh, read? Yeah, so there's a small error here. This should have been A equals 2. Already it was A equals 2 from the previous slide. But in any case, the question is, what happens at this point if P1 tries to read? So to summarize MSI versus MESI, like I already mentioned, in MSI, if a processor reads a cache line and then writes to it and keeps writing to it in the same core, then there is this this bus upgrade or bus redex signals uh, that are sent over, should be actually bus upgrade signal that are sent to other processes which are not actually needed, and therefore we have this MESI protocol which sends this which adds this exclusive state. So this is actually bus upgrade because it is a hit. Now, in the MESI protocol, if the cache line is in the E state, then it means that it's only present in that particular cache and not in other cores, and therefore you don't have to send any of these bus transactions. So it saves a lot of bus transactions if only a single processor is trying to do a series of reads and writes. So the next step for you is to figure out which of these are valid and invalid transactions in a MESI protocol.